Hello friends, welcome to yet another video of YouTube channel Tech Guru Gautam Prasad. In this video, we are going to discuss further into the details of series resonance circuit. This is quite interesting and you would love to go through this uh, study material. Resonance occurs in the circuit where the supply frequency causes the voltage across LC and C to be equal and opposite in phase. So that is the basis of resonance to happen. So this is RLC circuit. So the voltage across this L and voltage across this C are equal in magnitude, but they are opposite. They are opposite. So they will cancel each other, and the current will be limited only because of resistance in this circuit, and these two elements will disappear, or it will not pose any kind of impedance in the circuit. So this is a pretty interesting situation, and we have to explore what happens in this case. So series RLC circuit, we have XL equal to 2 pi FL, XC equal to 1 by 2 pi FC, or 1 by omega C. XL is omega L. So when XL is greater than XC, the circuit is inductive. When XC is greater than XL, the circuit is capacitive. So the total amount of the reactance in the circuit XT is equal to either XL minus XC or XC minus XL. It goes either way. Whichever is greater, we will have to subtract from that one. And the total impedance of the circuit Z is equal to a square root of R square plus XT square. So, inductive reactance against the frequency. Let us plot this one. So on the x-axis, you have taken frequency. On the y-axis, you have taken reactance, that is inductive reactance. As you know, XL equal to 2 pi FL. So this XL is directly proportional to the frequency. So this relationship is linear. This is the equation of a straight line. And so the line, uh, the curve, the graph is a straight line. The graph is a straight line. So reactance versus frequency is a straight line. Therefore, inductive reactance is positive and directly proportional to frequency. So we have to see now what happens in the case of uh, capacitive reactance. Now we know capacitive reactance Xc is equal to 1 by 2 pi Fc. So Xc is inversely proportional to the frequency. And that is why this graph or this plot between reactance and frequency is hyperbolic in nature because it's inversely proportional to the frequency. So that's the fact. The graph is hyperbolic. Now, if you take both together, then you will find on one side reactance in ohms, and your x-axis has the frequency. So, uh, this is the capacitive reactance, and this is the inductive reactance plot, and they cross each other at a point. And at this place, XL and XC are equal. XL and XC are equal. Now, this happens at a particular frequency that is called a resonant frequency, and it is represented by FR. Now, it is very interesting point. Now, towards the left of this uh, straight line, vertical straight line uh, uh, of this resonant frequency, you have on the left side is the capacitive area. So this area is capacitive. On the right side, you have inductive area. So the total reactance of the circuit is going to be inductive in this area and capacitive in the left side. So that is it. That is the behavior of the circuit, RLC circuit. And at the point of XL equal to XC, the point of intersection is XL equal to XC. At this point, if you equate it, 2 pi FL will be equal to 1 by 2 pi FC. And if you bring two F's together at one place, this equation becomes F square equal to 1 upon 2 pi L multiplied by 2 pi C. Now, this thing becomes 1 upon 2 pi square LC. And therefore, F will be equal to square root of 1 upon 4 pi square LC. So, F will be equal to 1 upon 2 pi square under the square of LC. So, this is called resonant frequency. And if you take the cyclic frequency WR happens to be 2 pi FR. So this will become 1 upon square root of LC. In radians, FR is in hertz and omega R is measured in radians. That's the difference. So here at this point, this is very interesting to understand this. Since reactance part becomes 0, XL minus XC or XC minus XL, whatever is the situation, both will become 0 and Z will be equal to R. So this is the point of interest, my friends. This point is interesting. Z becomes only equal to R. So at the resonance, the impedance of the circuit, series circuit, is at minimum value, and since the impedance of the circuit is at minimum value, the circuit current will go to the maximum value. The circuit impedance at the resonance is called dynamic impedance. This has been given extra a special name, and this is called dynamic impedance of the circuit. And depending upon the frequency, XC or XL, typically at low frequencies, will dominate the side of resonance. That's it. Impedance in the series resonant circuit. So impedance in totality varies like this. So here is, impedance. Impedance goes deep. It's a tub curve. So it goes deep to minimum point, and then it starts rising in the inductive area. So in the capacitive area, it goes on decreasing with the increase of frequency. And at after certain point, that is resonant frequency, if you keep on increasing the frequency, this your total reactance will start increasing after this frequency. So this is hyperbolic in nature. This shape is hyperbolic in nature, and you have to. You may also note that if the circuit impedance is at the minimum value at the resonance, then consequently the circuit admittance will be maximum. So as because impedance uh, uh, admittance is the inverse of your impedance. So when your impedance is going to the lowest value, your admittance is going to the highest value. That's the maximum value. Okay, and one of the characteristic of the series resonant circuit is admittance is very high. Admittance is very high. But this can be a bad thing because very low value of the resistance at the resonance means that the resulting current flowing through the circuit will be dangerously high. So this is a kind of threat in the resonant circuit. If if your impedance is going low, the current could rise dangerously. So we can recall from the previous tutorial about the RLC circuit that the voltage across the series combination is a phasor of VR, VL, and VC. Okay, that then if at the resonance two reactances are equal and cancelling each other, the two voltages representing VL and VC must also be opposite and equal, but they thereby they will be cancelling each other. Uh, with a pure component of the phasor voltage are drawn at plus 90 degree and minus 90 degree respectively. And then in a series resonant circuit, VL equal to minus VC. The resulting reactive voltage are zero and the supply voltage is dropped across the resistor only. Therefore, VR equal to supply voltage. The total voltage that we are applying from the supply side is, appearing across the resistor. So that is why VR is equal to V supply. So this is also important to note down. And it is for this reason the series resonant circuit is also known as voltage resonant circuit. Voltage resonant circuit. Why this name has been given? Because because the total supply voltage appears across the resistor, right? So here it is noteworthy that these two voltages across, uh, inductance and the capacitance cancel each other, and this behaves like a short circuit, as if these two elements are not existing, rather there is a short circuit between them. So it has been shown here in the another picture that this is just like a short circuit. Okay, since the current flowing through the series resonant circuit is the product of the voltage divided by impedance, uh, at resonance, the impedance is only minimum value, that is R, and therefore the circuit current at this frequency will be maximum value V upon R. So this is uh, the conclusion. And here is the plot of the resonant frequency. At resonance, circuit current is at the peak, and this is, for the lower frequency range, it is lower, but it keeps on gaining. This current starts increasing and increases very fast, but after a certain value, resonant frequency, it starts diminishing as well. If you increase the frequency further after the resonant frequency, the circuit current will go down and drastically go down. All right, so this is the behavior of the circuit current in the RLC series circuit, because uh, together with this, we have got the plot of reactance in this circuit, which is bar curve type that we had seen earlier. The frequency response curve of the series resonant circuit shows that the magnitude of the current is a function of the frequency, and plotting this onto the graph shows that the response starts at near to zero value and reaches to maximum value at the resonant frequency I max equal to IR, and then drops again to nearly zero as f becomes infinite. And this thus the frequency, thus the result of is that the magnitude of the voltage and voltage across inductor L and the capacitor C becomes many times the supply voltage, even at the frequency, but as they are equal and opposite, they cancel each other out at the resonant frequency. This circuit is also called acceptor circuit. Now, why it is called acceptor circuit? As the series resonant circuit only functions on the resonant frequency, and this type of the circuit is also known as acceptor circuit, because at resonance the impedance of the circuit is at minimum, so easily accepts the current whose frequency is equal to the resonant frequency. And you may also notice that the maximum current through the circuit uh, occurs at the resonant frequency, and it is limited only by the value of the resistance. The source voltage and the circuit current must therefore be in phase with each other at this resonant frequency. So at resonant frequency, whatever maximum current is there, that is in phase with the voltage. Okay. And then the phase angle, this is very important to note down. In fact, in some of the examinations, it is asked. So this is important to note down. Then the phase angle between the voltage and the current of the series resonant circuit is also the function of the frequency point Vi and Vr, okay, as shown in the figure below. So theta here below Fr means on the left side of the Fr value. The capacitive I leads Vs, the circuit current leads the source voltage. At Fr, I is in phase with Vs, but above Fr, inductive circuit is becomes inductive as we have discussed earlier. So I starts lagging Vs. Okay, so here is a complete picture of this. In this region, Xc is greater than XL. In this region, this value, uh, this is the frequency. We have plotted frequency on x-axis, and we have plotted the reactance on y-axis. So xc, for xc is greater than xl, this minus 90 degree, this angle has been plotted between angle between voltage and you know current. So it is minus 90 degree, because uh, it is taking leading current, or voltage is lagging basically. So voltage is lagging, that is why it is minus 90 degree. And as you increase the frequency, this you know uh, the capacitive nature is reducing, and so it is reaching to the point of frequency where they are equal. And after that, the circuit is becoming uh, uh, inductive, and the current becomes lagging by angle starting from 0, gradually increasing and going up to 90 degree. So starting from minus 90 degree, it goes up to the plus 90 degree. So that is the shift in the phase. So basically, this graph is discussing about the phase angle variation of current with respect to your voltage. Okay, hopefully you have understood the explanation. Now, bandwidth is something that must be studied in the case of resonant circuit. Bandwidth is, this half power zone. I will make you understand right now. What is this? This is also called minus 3 dB down maximum from the maximum. So this part, this is the frequency. In fact, at this frequency, this is basically 0.707. That means whatever current, maximum current is there at the resonance, if you divide that current by root 2, that gives you the RMS value. And at this RMS value of the maximum current, when divided by root 2, it is called minus 3 dB zone. And the frequency corresponding to this value, 0.707 max value, on either side of this resonant frequency is called bandwidth. So you have got on one side, left side, FL, lower side of the frequency, and FH is the higher side of the frequency, which is greater than FR. FL is less than FR, and the zone between FL and FH, lower side of the frequency and at the higher side of the frequency is called, bandwidth of the circuit. So series resonant circuit uh, is very much responsive between these two frequencies. This Between these two frequencies, it is made to operate because the response is very high. Current response is very high. So FR and FH, FR, FH, and FL, all these 3 points is better understood, I hope, to you. And this is how we define the circuit impedance. This is also called minus 3 dB or half power. At this point, as because your current is, you know, I max by root 2. So what is the power? P is I square R. So I max divided by root 2 ka whole square is going to be I square by 2. And if you multiply it by V, then the whole thing will be uh, uh, if you multiply it by r, then the whole thing becomes I square r by 2. So at the maximum point the power is I square r, and at this point fl and fh, the power is uh, 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 total power divided by 2, I square by 2. So that is why it is also called half power line. So I max by root 2 level of the frequency is called half power line. So this I max line, 0.707 I max line is also called half power line. All right. The frequency response of the circuit current magnitude above relates to the sharpness of the resonant circuit, resonance series circuit, and the sharpness of the peak is measured quantitatively and is also called quality factor, that is Q of the circuit. Quality factor or Q of the circuit. The quality factor relates the maximum or the peak energy stored in the circuit to the energy dissipated in the resistance. During each cycle of oscillation, meaning that the ratio of the resonant frequency to the bandwidth, and the higher the quality factor, the smaller the bandwidth. Q is equal to FR by bandwidth. So it is the rest quality factor is defined as FR divided by bandwidth. So this relationship itself, you know, justifies this line. The resonant frequency of the bandwidth and the higher the circuit quality. During the oscillation, meaning the ratio of the resonant frequency to the bandwidth, resonant frequency to the bandwidth, and the higher quality. So if frequency is higher, quality factor will have a higher value. If bandwidth is less, then also quality factor will have a higher value. So these are the two things that decides the higher quality of the uh, series resonant circuit. As the bandwidth is taken between minus 3 dB points, the selectivity of the circuit is uh, is the measure of its ability to reject the frequencies either side of these two points. A more selective circuit will have a more narrower bandwidth, whereas a less selective circuit will have a wider bandwidth. So if it is narrow, then it is more selective. It is If the bandwidth is wider, then it is less selective. So the selectivity of the series resonant circuit can also be controlled by adjusting the value of the resistance only, keeping all other components the same, since Q is equal to XL upon R. Q is equal to XL upon R. This can be proved. Uh, I'm not going to prove it right now because it is not needed. Now here there is a comparison of different types of frequencies and bandwidth. you know, current amplitude, and for different values of resistances. If you are taking a higher resistance, this peak is going to, flatten drastically. And if you are going to take a medium value of the resistance, then it is somewhere in the medium range. And if you take a very small value of the resistance, then it is going to be very high. So as you can see, this bandwidth is also getting affected, and this sharpness of the um, series circuit is also getting affected here. So you get a higher peak for the smaller value of the resistance. You get even less peak for the medium value, and least peak for the minimum value of the highest value of the resistance. The relationship between the resonant bandwidth and selectivity and quality factor for the series circuit is being defined as XL equal to XC omega L. This omega are equal to this thing we have already seen, and I max equal to V max divided by Z, and at resonance, this Z is equal to R, so that is becomes maximum. At half power Pm by root 2, I is equal to Im by root 2, that is 0.707 Im, and Z equal to root 2 R, Z equal to root 2 R, X equal to minus R, X equal to minus R capacitive, WL equal to 2R by 2L, square root of R by 2L plus 1 by LC. This can be proved, but it has not been proved here. Okay. Upper cutoff frequency at half power Pm by root 2, I equal to Im by root 2, that is 0.707 Im, Z equal to root 2 R, X equal to plus R, uh, inductive, and WH equal to plus 2R by 2L, square root of R by 2L whole square plus 1 by LC. Bandwidth equal to FR by Q, FH by FL, FH minus FL, or R by L, or R by 2 pi L. So, this is in radians, this is in hertz. And quality factor is equal to omega RL divided by R, or XL by R, or 1 by omega R CR, XC by R, or equal to 1 by R square root of L by C. So these many ways are there to define the quality of the series circuit. Series resonance example number. This is a question basically, and you have to solve it, but we will solve it in the next video. Thank you very much uh, for being with me up to this point. If any confusion is there to you, you can write in the comment box, and definitely I would like to help you if you at all you have any confusion. Thank you very much. Stay tuned with me for more videos. Keep on suggesting me in the comment box to have a better video.